Hello and welcome to lecture 4 of the intensive course on categories and modules. Speak up. Okay, great. So this part, lecture 4 is really in a sense a continuation of lecture 1. So in lecture 1, Stefan Segave told you lots of things about categories and functors and natural transformations. And then in lectures 2 and 3, we moved on to rings and modules, and the categories played less of a role. Now in lecture 4, we go back to the world of categories with a vengeance. So before I get into the details, let me do a couple of sort of administrative things. So there are typed lecture notes to accompany this lecture 4, which are also linked to from the ELO website on the sort of next to the videos. So I will not there are some proofs where I will skip some details, and so the details can then be found in these lecture notes. The lecture notes also contain more precise references. So again, I will not write up every detail of every proof or whatever on the board. In the notes there are references, well, in the notes there are more details and also references to the notes of Lenny Tellman, so giving you the precise chapter and verse, so you can find there things that you've not seen before. So if the first time that you met a category was in Stefan's lectures a few days, in the last couple of days, then you may find the things that we do in this lecture a bit difficult, because I'm going to be assuming that by this point you're somewhat comfortable at working with categories, functors, and natural transformations. If you don't feel comfortable about working with these things, then I very much recommend that you go and take, for example, Lenny's notes and work through some of the exercises there until you're a bit more familiar with things. But equally, you could just sort of stick along with what's happening here and work out the details when you get lost. So that's the background. So I want to give a convention for this lecture as well. So I'm going to generally avoid using contravariant functors, because there'll be a lot of places where we have what we should call co- and contravariant functors, and it can get very confusing. So what I find things less confusing if I stick to using covariant functors, and then if I need a contravariant functor, I put an op on the category. So this is a convention I will stick to. So all functors in these lectures are going to be covariant. Okay, so that's all the sort of administrative things out the way. So this is going to be, I think, lecture 4 will come in hopefully 3 segments. The first will be Yoneda's lemma, which is this one. Then there'll be a segment on limits and colimits, and finally a brief section on adjunctions. So Yoneda's lemma. So the starting point for this is a remark that appeared in lecture 1, which was concerning representable functors. So Stefan defined how given an object, then if C is an object of a category, then hom blank C is a functor, and he said this is a representable functor. And so that's really where I'm going to pick up the story here. But I'll remind you of that. I mean, let's not assume that you instantly recall everything from the previous lectures. So let's see the category. And let C in the object of C. So then we have a functor, so then we have hom, so I'm going to write this as hom C. This is a capital C, make it a bit bigger, blank comma C. This is a functor from C op to set. You can think of it as a contravariant functor from C to set, but I prefer to think of it as a covariant functor from C op to set. So in Stefan's lectures, this was written as C blank comma C, but I'm sticking to this hom notation for today's lecture, I have to make a choice, and that is the choice that I will make. So let's remind ourselves what this thing does. So firstly, it's a functor. We should say what it does on objects and also what it does on morphisms. So on objects, so it's going to send an object D, it's going to go to the set hom in C from D to little c. So it just sends an object to the set of homomorphisms from D to C. And what's it going to do to a morphism? Here we have to be a little bit more careful. So given, say, F from D to E in C, so this is, we should think of this as a morphism the other way in C op. So what's going to happen? So we're given a map from D to E, equivalent, you can think of this as a map from E to D in C op. And then we want to give a map from hom E, C to hom D, C. And so how are we going to do that? The only reasonable thing to do is composition. So let's see if we can write this thing down. So we have a map from E to C, and we're going to send that to, well, what can we do? We can go from D to E, and then from E to C. So I guess if this is called G, then here is G and here is F. So in short, we can write this as, so this map, this composite map here, I'm sorry, I'm running a little low on space. This composite map here is then, what is it, G composed with F. There's always, the thing that confuses me most is getting these the right way around, which is unfortunate because that's basically what this lecture consists of. Okay, so what we've just seen is we take any category and we take any object of the category, then this hom from blank to the object gives you a functor from C up to set. So that's the starting point. So what we can now do is we can sort of turn this thing itself into a functor in a way which I'll explain in a second. So I'm going to define the category fun C op set. So this is the category, so this is supposed to be the C. So the objects are, they're functors from C op to set, or if you like, they're contravariant functors from C to set, and the morphisms, if you remember how these things work, it should not surprise you that the morphisms are natural transformations. Rob, do you think I'm writing big enough? Or is this getting, am I getting a bit small? We'll see.
Probably wouldn't do any harm to make it a little bit bigger.
Okay, I'll try and write a little bit
Looks
bigger.
clear on this very small screen.
Yeah, we'll see. I'll try and write bigger. Sorry. Okay, so the morphism, so the objects are functors and the morphisms are natural transformations. Of course, I should tell you what the units are, and I should tell you what the composite of the morphisms are, but I'm not going to write this down explicitly because I think that you can probably guess them very easily if you think about it a little bit. So here is my category. In some sense, it's a sort of, I don't know, a leveled up version of C. So the objects of my new category are the functors from C to set, and the morphisms of my new category are the natural transformations. And so now we're going to define a functor. This is the Yoneda functor, which is the same Yoneda, of course. And this is often written as H, and this goes from C to our functor category. So maybe I should say, I mean, I'm sort of beginning with let C be a category. This is sort of a very general thing. If you're looking for an example to keep in mind, I think my favorite is perhaps to take C to be the category of topological spaces. Everything I'm saying is, of course, working in complete generality, but if you take C to be, if you want something a bit more concrete to think about, then taking C to be topological spaces or manifolds or something is a nice example for this sort of machinery. Okay, so we're going to define the Yoneda functor. So to say what it does on objects, we're going to use the construction here. So we're going to send an object C. It's just going to go to the functor hom blank comma C. Well, we sort of, I think, well, we said exactly, we said over here exactly that this thing is a functor. We said what it does on objects and we said what it does on morphisms. So, okay, that's what our Yoneda functor does on objects. We still have to say what it does on morphisms. So this one is always a little bit more confusing. So on morphisms, so remember that all functors are covariant. In particular, this functor is covariant. So it's not going to switch the directions of the arrows. So if we have, say, a morphism from F from C to D in our category C, then what's going to happen to this? Maybe I need more space at the bottom of the board. We will see. So this should be then a natural transformation of functors. So, and it should be a natural transformation from this guy to the guy with a D in. So let me write this out. So this is going to be a natural transformation from hom C blank comma C to hom. And what's it going to do? Again, it's going to basically work by composition. So remember how a natural transformation is defined. So for every object of C op, then say we take an object E of C op, then supposing we have a map, say, from E to C in here, then it should give us a map from E to D. What's the map from E to D going to be? Well, here we're going to compose. So supposing I call this thing G maybe, then I'm going to send it to E goes to C by G, and then C goes to D by F. Okay, so notice, so it's important, like these, I find it very confusing, like not to mix up this construction and this construction. Notice that the composites go on the other side. Sort of this, if this was our old morphism, here we stuck the F on the left, and here we stuck the F on the right. And this is, well, you have to keep track of these things. So my claim is that this is then a natural transformation. I've told you what it does. I've told you what it does for every E. I've told you what it does. To check that it's a natural transformation, you have to check that a certain diagram commutes. I'm not going to write out the diagram, because it just comes from the definition. So a very important exercise. So check that this construction is actually a natural transformation. Okay. If you've seen everything before, of course, you don't need to do the exercise. But if you're at all unfamiliar with these things, then I strongly recommend this exercise, because it's a very good way to make sure that you've got all of the directions of all the arrows the right way around in your head. You'll also see exactly how this sort of different orders of compositions, how these fit together to yield you a nice natural transformation in this way. Okay. So we've done lots of things, but what we've ended up producing is this crucial Yoneda functor here. Maybe I'll give myself a box. I would do it in color, but I don't think I have any color. Okay, so here's the Yoneda functor. What's the Yoneda lemma? This says that this functor H.
Actually, there is a color in this box here.
Ah, wonderful. Thank you very much. I shall make things. Very nice. The functor H we defined over there. Is fully faithful. Okay, so that's the lemma. I'll remind you in a moment what fully faithful means. As often happens, the thing which has lemma in front of it is more useful than many statements that have theorem in front of it. So this result is the reason I use category theory sort of almost every day in my research is basically comes down in the end to this lemma. If it weren't for this lemma, then I would probably not have bothered learning about categories. So it's a very useful thing. I will try to explain in the second part of this talk one of the sort of how this thing can be so useful. But let me remind you what fully faithful is. So this was in lecture 1, but it's maybe given it's so important. So fully faithful means, so formally what it means is that for any two objects of C, let me write this here, so i.e. for all C and D on objects of C. So we have an induced map which goes from Hom in C, from C to D, to Hom. I better call this just F for a moment, because otherwise the notation gets terrible. Okay, so because the Yoneda functor is a functor, it induces a map on the Hom sets like this, and being fully faithful means that this map is a bijection. Okay, maybe I'll steal another piece of colored chalk. But being fully faithful is exactly the same statement as this map is a bijection. This is a formal definition. What's a good way to think about full faithfulness? Full faithfulness to me is something like being injective. So a couple of reasons. So obviously it's a statement about a functor. So it's I mean, it's not the same. It is not the same as being injective on objects or something like this. Generally, whenever you're doing things with categories and functors, sort of set theoretic notions don't translate directly because you sort of want to keep. You have lots of isomorphisms floating around. But this plays, so being fully faithful behaves rather like injectivity. For example, if two objects, if you have two objects in here which become isomorphic, then in fact they were isomorphic. So this is the key property of fully faithful things. Another way to think about it, another reason why full faithfulness behaves like injectivity is that, as you may remember from lecture 1, a functor is an equivalence of categories if and only if it's fully faithful and essentially surjective. Essentially surjective, of course, is roughly like surjectivity, so fully faithful is sort of the injectivity half of the classic statement for sets that are a map of sets is a bijection, if and only if it's injective and surjective. Okay, so this is the statement of the lemma. What about the proof? So I'm afraid I'm not going to give the proof. I've tried to lecture the proof of Yoneda's lemma in the past, and it always becomes very confusing on the blackboard. The proof is essentially a sort of a purely formal thing. It's just a matter of pushing arrows around on the page. But it's not something that is very useful to see somebody else do. It's really something that you want to sit down and try to do yourself. So the proof is an exercise. So I recommend, so I think you should definitely try to do this exercise. If you get stuck, well, there are proofs in many places online, but a nice proof is given in Lenny's lecture notes, so theorem 7.8 of physics. Okay, so these notes are linked to on the relevant ELO page, and this reference is also precisely given in the printed lecture notes. Okay. Generally, yeah. So I think, yep, that's all that I want to say about this. So why is this lemma so important? So another way to say that, so another equivalent notion, another equivalent condition for your functor being fully faithful, you can think of it as saying that it makes this category C into a full subcategory of this functor category here. And so if you have some category that you find that sort of you want to understand objects in, then it can often be useful to think of C as living inside this larger category here. So this comes up, for example, enlarging the category of objects you live in is a standard technique in mathematics. For example, if you're trying to do some differential geometry and you're working with differential forms, then by enlarging to the world of currents, then you can like solve lots of nice problems, and that's sort of an analogous thing. Also in this case, so an example closer to home which we'll meet, you may well meet in the next year, if you're working with, say, schemes or if you're doing algebraic varieties, algebraic geometry, then this machinery leads you naturally to the notions of algebraic spaces and algebraic stacks, which are very useful and sort of more flexible versions of schemes and this kind of thing. Okay, so, but this is all getting a bit ahead of ourselves, so I want to give a sort of a more concrete, down-to-earth example. It's the last part of this. So I want to give a sort of extended example. To show the kind of thing that you can do with Yoneda's lemma. So I'm going to work in topological spaces. More precisely, I'm going to work with manifolds. So I'm going to fix an integer n, which will be at least 0. The n equals 0 case is not so interesting, but never mind. And write MFD manifolds of dimension, for manifolds of dimension n. And here I only mean topological manifolds. So there's no smooth structure or anything like this. Okay? And so, as before, we have a Yoneda functor which goes from the category of manifolds. So we can take this to be our category C, then we get a Yoneda functor which goes from the category of manifolds, maybe we should underline it as it's a category, to this collection of functors. I'll write this down in a sec. What else can we do? What else can we do? We can look at a subcategory of this. So let D be the full subcategory of M sorry, the full subcategory of this manifolds and with objects are isomorphic to the open unit disk in Rn. Okay, so I can't remember if we've met the notion of a full subcategory, so let me quickly remind you of that now. So a full subcategory is just, so if you have a category, say manifolds, to take a full subcategory, you're taking a subset of the objects, and then to define the homomorphisms, you just take the homomorphisms from your original category. So in other words, the maps in your subcategory are, you just define them to be whatever the maps are between your objects in the larger category. Okay, and so in particular, if I have a full subcategory, there's a natural map from D, so there's a natural map to the larger category. So I suddenly have a natural map from D to manifolds of dimension n. Moreover, this map is going to be fully faithful, because being fully faithful says that the map on Hom sets is a bijection, and I defined the Hom sets in here to be just the Hom sets in here. So nothing too much happens there. I also have my Yoneda functor, H, which goes to okay. I can then make another functor using this full subcategory. I've gone and run out of space slightly here. I'll just write it down here. Okay, so what's happening here? So this last arrow, sorry that it became a little bit broken up. What this last arrow does is it just restricts a functor. So if I have a functor from manifolds to sets, then I can just I can say, well, I only care what it does to objects in this subcategory here. And so that gives me a functor between these two categories. Again, of course, to write down the details carefully, there are quite a number of things to check. This restriction process actually makes sense. These are definitely good things. I mean, you should definitely check these for yourself, but they are not fun to write on the board. Okay, so we have a chain of maps of functors. So Yoneda's lemma, which alas we just erased, tells us that this arrow is fully faithful. Also, we know that the inclusion of a full subcategory is by definition fully faithful. However, what about this last arrow here? This last arrow is not fully faithful. Maybe I should give this a name. I can call this R, got a restriction. So the functor R is not fully faithful. Okay, so this is, I mean, in general, if you take a functor category and you just do some sort of restriction operation, there's sort of no reason why it should be fully faithful. In general, it won't be. On the other hand, to actually write down examples is more tricky. In this case, okay, the example, there's a rather artificial example which shows that this thing is not fully faithful. It comes down to like playing around with the empty set. Shall I write it here? Yeah. So what do we do? So I want to give, so to prove that it's not fully faithful, I want to give two objects here which are not isomorphic, but which become isomorphic here. That was one of the sort of properties of being fully faithful that I discussed over here. So, for example, if I define a functor, say f0, from manifolds up to set, and what am I going to do? This is a really stupid functor. This is going to send every manifold to the empty set, and well, now you can guess what happens to the maps. So every map goes to the unique map from the empty set to itself. I can make another functor f1, which goes from manifolds to sets. This is almost a stupid functor. So this is going to be defined to be Hom in the category of manifolds from blank to the empty set. Okay. So these two functors, what you'll find is that if you take any non-empty manifold here, then the functors take the same value. Okay, I should also, here you get the empty set out, and here will you get the maps from a non-empty manifold to the empty manifold, which is the empty set of maps. So these functors are almost exactly the same. The only place where they differ is what happens if I plug in the empty manifold. If I plug in the empty manifold here, I get the empty set. If I plug it in here, I get the unique map from the empty set to itself. Okay, so it's very artificial, but indeed, these are not equal. But R of F0 is equal to R, or is isomorphic to R of F1. Okay, so I'm not going to prove this in detail, but the point is that the objects in here are all non-empty, right? Because they're all the manifolds in here are by definition isomorphic to this unit disk, so in particular they're not empty, and so very formally these functors can have to be the same. Okay, so this was a very silly example, but at least it shows that these things are indeed, that this functor is indeed not fully faithful. So the next result, so this perhaps makes the final result somewhat surprising. So a lemma, so the composite so from manifolds and to is fully faithful. Okay, so I'm going to, am I going to sketch or am I going to prove? I'm going to, I think, just briefly sketch how the proof of this goes, because I don't want to use up too much more of your time. I want to talk, but I do want to use some time to say what's going on here. Like why is this a useful, what is this statement saying? Okay, so remember what happens if I take a manifold here. So let's just remind ourselves what happens. So M maps to basically HOM in the category M, the category of manifolds, from blank to M. But then we restrict to, so we only evaluate this on things which are disks. So in other words, given a manifold, what its image is telling us is really all of the possible maps from the unit disk to M. So M is some n-dimensional manifold, and then what this composite gives you is all the possible ways of throwing unit disks at M. And so another way to think of this statement is saying that a manifold is determined by all the maps from unit disks to it. So a manifold is determined by all the maps from a disk to it. Say a manifold M is determined by all the ways of mapping a disk to it. Now, of course, this is a vague statement, and if you interpret it in a silly way, it's just going to be false. This is the precise statement which is not false. And so, how does this proof go? So, fully faithfulness, so full says that the map on HOM sets is surjective, and faithful says that the map on HOM sets is injective. So checking that the map on HOM sets is injective is very easy. It's given in the note, but it's sort of if you just follow your nose, then the answer drops out. Also, it doesn't really use that we're working with manifolds. If we replace this by topological spaces in general, then we still have the faithfulness. So the faithfulness is a sort of boring thing. It's not really, nothing much is going on. The important part is the fullness, the fact that the maps on HOM set are surjective. So remember, that's saying that if I have, say, manifolds M and N, then every natural transformation between the corresponding functors comes from a map between the manifolds. So somehow from every natural transformation of functors, you can reconstruct an actual, honest, continuous map of manifolds. Okay, and so the way the proof works is, well, you take a cover of your manifold by some open disks, and then you evaluate your natural transformation on objects of that cover, and things go through in a reasonable way. So well, I don't want to put this as an exercise. So the last things I think you should try to do are, firstly, to read through the proof of this in the notes and make sure that it makes sense, and also an exercise, or to think about. So why does this fail? If I replace the category of manifolds by, for example, the category of topological spaces. And so, to give a sort of hint for this, if you, for example, take your topological space to be something like the Cantor set, and then if you take the Cantor set, and then on the other hand you take some discrete uncountable set, then you're going to, then you will be able to build an isomorphism between these functors, but of course it will not correspond to a continuous matrix between these topological spaces. So that's really the key thing. Okay, so I think that's everything I want to say about the Yoneda lemma, so I shall end here.